How life on Earth affects its inner workings. Well, one of the things we'll be talking about today is granite, and I was always amazed at this image of the huge ancient giant footprint found in what is a piece of granite rock, and it was obviously made when the granite was very soft. Very strange, that must have been millions of years ago. The granites represent melted sediments that were deposited at the surface of the earth. And we'll be talking about that later in the article. The idea that sediments might still record the first rise of oxygen on Earth, despite having been heated up and melted to create granite. You can imagine the temperature of this granite when it was still hot. Now, going back to reading the research, this is on phys.org by Robert Perkins. California Institute of Technology has this to say: how life on Earth affected its inner workings. It's well known that life on Earth and the geology of the planet are intertwined, but a new study provides fresh evidence for just how deep, literally, that connection goes. Just in thought, because of the fact that I don't want to lose my train of thought, it just came to me that we've had various earth changes and catastrophes, destructions, having to do with asteroid strikes. Even the air was on fire, even the atmosphere was boiling, and the asteroid strike, of course, caused a tremendous increase in thousands of degrees Fahrenheit. It was the cause of earthquakes and volcanic eruptions, and obviously the rocks would be melting. And we don't know if this footprint was made at a time of one of these impacts and earth changes and heated rock because of some type of an event. It could be. We know that there were various times when maybe a few individuals were perhaps rescued or saved themselves in some way. A lot of the times we've heard in archaeology of the underground dwellings. Also the fact that the ancients were very keen on keeping their eyes on celestial bodies and constellations, because they believed that every few thousand years there are celestial bodies that could impact the earth, and that they had to protect themselves from that. And the only way they knew, obviously, was perhaps hiding in the earth for security, to save themselves. This is also one of the prophecies in the book of Revelation, that the destruction will be so great that men will want to hide in the mountains, and the crags and the openings of the mountains and the rocks to save themselves, meaning caves and underground dwellings. Now, going back to this, the life on Earth and the geology of the planet are intertwined, and the new study provides fresh evidence for just how deep that connection goes. Geoscientists at Caltech and UC Berkeley have identified a chemical signature in the igneous rock, recording an onset of oxygenation of Earth's deep oceans, a signal that managed to survive the furnace of the mantle. This oxygenation is of great interest as it ushered in the modern era of high atmospheric and oceanic oxygen levels, and is believed to have allowed the diversification of life in the sea. Their findings, which were published in the Proceedings of National Academy of Science on April 11, supported a leading theory about the geochemistry of island arc magmas and offer a rare example of biological processes on the planet's surface affecting the inner Earth. Island arcs are formed when one oceanic tectonic plate slides beneath another in a process called subduction. The subducting plate descends and releases water-rich fluids into the overlying mantle, causing it to melt and produce magmas that ultimately ascend to the surface of the Earth. Well, and when magmas ascend, we know that that's when the volcanic process begins. The process builds island arc volcanoes like those found today in the Japanese islands and elsewhere in the Pacific Ring of Fire, and eventually, through plate tectonics, island arcs collide with and are incorporated into continents, preserving them in the rock record over geological time. The most abundant magnetic or igneous rocks are basalts. They're dark-colored and fine-grained rocks commonly found in lava flows. Most basalts on the Earth today do not form at island arcs, but rather at mid-ocean ridges deep underwater. A well-known difference between the two is that island arc basalts are more oxidized than those found at mid-ocean ridges. A leading but debated hypothesis for this difference is that oceanic crust is oxidized by oxygen and sulfate in the deep ocean before it's subducted into the mantle, delivering oxidized material to the mantle source of island arcs above the subduction zone. But Earth is not thought to have always had an oxygenated atmosphere and a deep ocean. Rather, scientists believe the emergence of oxygen, and with it the ability for the planet to sustain aerobic life, occurred in two separate steps. The first event, which took place between 2.3 to 2.4 billion years ago, resulted in a greater than 100,000-fold increase in atmospheric oxygen, O2, in the atmosphere to about 1% of modern levels. Although it was dramatically higher than it had previously been, the atmospheric CO2 concentration at this time still was too low to oxygenate the deep ocean, which is thought to have remained anoxic until around 400 to 800 million years ago, and around that time atmospheric oxygen concentrations are thought to have increased 10 to 50% of modern levels. That second jump has been proposed to have allowed oxygen to circulate into the deep ocean. Quote, if the reason why modern island arcs are fairly oxidized is due the presence of dissolving oxygen and sulfate in the deep ocean, then it sets up an interesting potential prediction, says Daniel Stauffer, Caltech PhD of 2014, one of the authors of the paper and an assistant professor of Earth and Planetary Sciences at UC Berkeley. Quote, we know roughly when the deep oceans became oxygenated, and thus, if this idea is right, one might see a change in how oxidized ancient island arc rocks were before versus after this oxygenation, end quote. To search for the signal of this oxygenation event in island arc igneous rock, Stolper teamed up with Caltech Assistant Professor of Geology Claire Boschultz, who studied modern and ancient arc magmatic rocks. Stolper and Boschultz combined through published records. They combed through published records of ancient island arcs and compiled geochemical measurements that revealed the oxidation state of arc rocks that erupted tens of millions to billions of years ago. Their idea was simple. If oxidized materials from the surface is subducted and oxidizes the mantle regions that source the island arc rocks, then ancient island arc rocks should be less oxidized and thus more reduced than their modern counterparts. Quote, it's not as common anymore, but scientists used to routinely quantify the oxidation state of iron in the rock samples. Boschultz says, so there was a wealth of data just waiting to be re-examined. Their analysis revealed a distinct signature, a detectable increase in oxidized iron in bulk rock samples between 800 and 400 million years ago. The same time interval that independent studies proposed the oxygenation of the deep ocean occurred. To be thorough, the researchers also explored other possible explanations for this signal. For example, it is commonly assumed that the oxidation state of iron in bulk rocks can be compromised by metaphoric processes, that is, the heating and the compaction of rocks, or by processes that alter them at or near the surface of the Earth. Boschultz and Stolper constructed a variety of tests to determine whether such processes had affected the record. Some alteration almost certainly occurred, Buchholz says, but the changes are consistent everywhere these samples were taken. The amount of oxidized iron in the sample may not have been sufficient for after cooling and solidification, but it appears to have been sifted in a similar way across all samples, she says. Stolper and Buchholz additionally compiled another proxy, also thought to reflect the oxidation state of the mantle source of arc magmas. Reassuringly, this independent research, the record, yielded some similar results to the iron oxidation state record. Based on this, the researchers proposed that the oxidation of the deep ocean impacted not only the Earth's surface and oceans, but also changed the geochemistry of a major class of igneous rocks. This work complements earlier research by Buchholz that examines changes in the oxidation signatures of minerals in igneous rocks associated with the first oxidation event 2.3 billion years ago. She collected sedimentary type or S-type granites, which are formed during the burial and the heating sediments during the collision of two landmasses. For example, in the Himalayas, where the Indian subcontinent is colliding with Asia. The granites represent melted sediments that were deposited at the surface of the Earth. I wanted to test the idea that sediments might still record the first rise of oxygen on Earth, despite having been heated up and melted to create granite, she says, and indeed it does. Both studies speak to the strong connection between the geology of the Earth and the life that flourishes on it, she says. The evolution of the planet and of the life on it are intertwined. We can't understand one without understanding the other, says Buchholz. The PNAS study is titled Neoproterozoic to Early Phanerozoic Rise in the Island Arc Redox State due to Deep Ocean Oxygenation and Increased Marine Sulfate Levels. This is on phys.org by Caltech. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.